Hi, this is Group 8 for Design Optimization. I'm Raihan, and our group focuses on the optimization of the wind turbine blade design. Our system consists of three subsystems. First is blade width design, second is life cycle cost calculation, and the third is generated energy calculation. From the diagram on the right, subsystems 1 and 3 share the design variable blade span R. Additionally, subsystem 2 provide cost feedback to both subsystem 1 and 3, influencing the viability of their outputs. Looking at the problem from a system-level perspective, our objective is to design a wind turbine that is cost-efficient, lightweight, strong, and capable of generating maximum power. We approach this problem by optimizing the maintenance interval to maximize revenue. We are moving on to the optimization and mathematical model of our system. Our subsystems use both analytical methods and finite element simulations to obtain the optimal solutions, and optimal solutions from each subsystems are then fed into a system-level optimization process, which ultimately determines the overall optimal solutions in terms of revenue and maintenance interval. We made following assumptions, like cost parameters are held constant, power output degradation follows an exponential decay, maintenance actions are associated with repair expenses, and the economic feasibility ratio of 0.268 is assumed.
Hello, I'm Chenghao Li. Next, I'll introduce the parameters in our optimization model. You have 14 types of parameters in the optimization model, including things like three different materials when designing the blade of the turbine and the corresponding unit cost, and the labor salary when building the turbine. These are all investing cost parameters. We also have electricity price, calculating the earnings. The results from sub 1 and sub 3 are pre-optimized and are used as inputs into the system-level model. The primary variables is the maintenance interval because it is related to both the energy generation lost and the investment. We also got several intermediate variables, including different costs like material costs and labor costs. The total cost of each interval is defined as the sum of all of them. The P sub sum here is the average power between every two maintenance days.
Hello, my name is Jie. For the constraint, the maintenance interval must be longer than 20 days but shorter than 7,300 days, equivalent to 20 years. To ensure economic feasibility, we impose a cost constraint. The total cost should not exceed 26.8 of total revenue. This threshold is based on the findings from previous studies. Finally, our objective function is to maximize net revenue, which is equivalent to minimizing the difference between total cost and revenue. Then we start to introduce our optimization method. We use MATLAB Global Optimization Toolbox to imply our genetic algorithm. GA is well suited for solving nonlinear, non-convex optimization problems where traditional gradient-based methods often struggle. One of these key advantages is that it does not require derivative information, making it particularly effective for handling empirical constraints. To enhance our performance, we incorporate several additional strategies. Constraint handling through penalty function to ensure feasible solutions, a random initial population to reduce the risk of convergence to local optimum, and crossover and mutation technologies to maintain diversity in solution space.
This is Chuan. Here we present our optimization result. From the table, you can see the first three rows represent different parameter settings by changing the average labor salary and the cost of the steel, whereas the last two rows represent different initial points under the same parameter setting as the row 1. Despite those variations, each run yields an optimal maintenance interval of 253 days, and this consistency indicates a robust optimum and a single dominant maximum in the cost revenue model, even though the absolute revenue and the constraint activity naturally vary with different parameter values. Moreover, the figure to the right shows you that altering certain parameters reshape the revenue curve, but still kind of preserves a global maximum in the same vicinity. Even though the revenue curve exhibits multiple local peaks. The significantly higher peak near 253 days still attracts the GA solution because of its combination of selection, crossover, and mutation can effectively avoid getting stuck in those local optima. So despite those bumps, the global optimum at 253 days still consistently emerge.
Now that we have obtained our optimization result, we move on to the parameter and constraint sensitivity analysis. This analysis helps us understand which input parameter and constraint have the greatest influence on revenue. To conduct a sensitivity analysis, we relax selected parameters and constraint by 10%. Then we can compute both parameter and constraint sensitivity coefficients. We test three key parameters: electricity price, cost of repair, and wind speed. According to our results, the parameter with the smallest perturbation had more significant variation in the objective function than those with larger perturbation. That is, the electricity price is the most sensitive parameter for the global objective function, which is shown in the table. Next, we evaluated the sensitivity of the system to key constraints, specifically how tightening or loosening the bounds on key variables impacts revenue. We perturbed the allowable range of pitch angle, tip speed ratio, and power coefficient constraints. Similarly, the CP constraint is the most sensitive constraint for the global objective function, which is also with the smallest perturbation.
In this slide, we are showing how our optimized maintenance interval in annual revenue compares to well-established findings in both academic literature and industry reports. To the left, we can see our interval of 253 days fits right within the standard best practice offered by those three academic articles, and those are highly cited articles. And to the right, you can see we cross-reference the Louisiana Department of Energy and Natural Resources Technology Assessment Division data, which provides annual revenue figures for different wind classes. Our result is around 10 million, and you might notice that the annual revenue figure is somewhat higher than the revenue figure reported in the benchmark study. The primary reason for that is that our model focused solely on the operational aspect and did not include installation costs. In comprehensive economic analysis, installation costs can form a significant part of the overall project expense, and those costs can kind of reduce the net annual revenue. So in short, all of those references we have here, from industry assessments to advanced optimization papers, confirm that our model is not only theoretically sound, but also closely matching real-world performance benchmarks in the wind energy sector.
Hello, I'm Sumukha. In this slide, we shall begin by comparing the performance of individual subsystems to the results of integrated system-level optimization. In subsystem 1, which focused on blade rate optimization, the minimum blade mass was approximately 2.4 metric tons for 30.5 meter span. However, the system-level optimal design selected a 38-meter blade with slightly lower mass of 2.2 metric tons. This indicates a trade-off accepting a larger blade to gain better overall performance at the system level. For subsystem 2, we initially achieved a very high lifecycle revenue of 21 billion due to idealized assumptions, but when we integrated the system model, the realistic revenue dropped significantly to around $10.4 million, showing the uncoupled optimization can heavily overestimate benefits. In subsystem 3, we saw a peak power output of 2.576 kilowatt at 38 meter with high power coefficients. However, at system level, the power output dropped drastically to about 51 kilowatt. This is due to trade-off made between weight, cost constraints, and again highlighting the importance of integrated optimization. So the overall system optimization balances all objectives and demonstrates the true optimum only emerges when all subsystems are considered together. Engineering insights. From our engineering analysis, we drew several key insights from each subsystem. For subsystem 1, although the blade was minimized, the genetic algorithm showed some variability in the solution, pointing to a trade-off between achieving low mass and maintaining structural integrity. In subsystem 2, we found that maintenance intervals significantly influence revenue, and the results are highly sensitive to input assumptions. In subsystem 3, the multiple combination of tip speed ratio and blade pitch could yield similar power outputs. This indicates the flexibility in aerodynamic design, but also suggests a need for smart selection based on system level goals. Future directions. Looking ahead, we've identified few main directions to enhance this work. First, we aim to develop fully coupled multi-objective optimization framework that integrates all three subsystems, balancing weight, cost, power generation more effectively. Second, we will focus on improving optimization robustness. This means scaling up genetic algorithm with larger populations and generations and exploring more advanced techniques like surrogate modeling or Bayesian optimization. Third, incorporating real-world variability is essential. We plan to model uncertainties in wind condition, material properties, manufacturing tolerances. Stochastic constraints and probabilistic failure models like variable distributions will help the reliability and give better results under extreme conditions. Finally, we want to expand the cost model to cover the full life cycle, including decommissioning and recycling, and quantifiable environmental benefits. We will also broaden the design space by exploring more blade geometrical designs and assessing reliability across a wider range of scenarios. Thank you.